Hi, welcome back. This is the homework sheet discussion, homework sheet 2, discussion part 1. We completed homework sheet 1 under two parts. Now we are going to complete homework sheet 3, atomic structure, homework sheet 2, atomic structure, part 1. Actually, I wanted to do this discussion as an online live class, but then it is quite difficult to find a time slot. If I am free, then you are not free. If you are free, I'm not free. Because these days I am quite busy with that 20-25 people. So then now I found a free time slot. Therefore, I decided to do this one, do this recording, and then share it with you. So I think it is okay with you. Anyhow, you need to understand your mistakes you have done in these questions. But doesn't matter, live or recorded one. Sorry. Let's move to discussion. This is homework sheet 2, part 1. Atomic structure. Homework sheet 2, atomic structure. So I know then you have already tried all the questions. Then you are waiting for your mistakes. Identify mistake. Okay, let's go to question number 1. An electron is excited from ground state to n equals 3. Which of the following statement true? Ground state to n equals 3. I'm talking about question number 1. Let's have three energy level, first three energy levels of hydrogen. This is first energy level, second and third. It excited from the ground state to n equals 3. Earlier it was in ground state, lowest energy state, but now it is in the third energy level, which has high energy. Then if I take the energies of these sub energy levels like E1, E2, E3, energy increases in this manner. It takes more energy to ionize the electron from n equals 3 than from the ground state. This is about like this. I mean, here I take it like this also. This is your nucleus of hydrogen atom, first energy level, second energy level, third energy level, right? Earlier, your electron was in this first energy level. Then to ionize this electron, you have to supply certain energy. Let's say it is I1. You are going to ionize electron from the first ionization, first energy level of hydrogen atom. But now this says electron is in third energy level. What if you have now electron in the third energy level? Now you are going to remove that electron. Let's say it is I1 dash or something. That's also first ionization energy, according to this. Correct? You try to remove electron from the first energy level, I1. You try to remove that electron from third energy level, I1 dash. So which one out of these two is large energy? We can understand it very clearly because if there is a stronger attraction between the nucleus and outer electron, that is where you have to supply more energy to remove the electron and ionize the atom. Then which one is having a strong attraction? I told you if there is a two oppositely charged species, this is plus, the electron is minus, plus and minus. The force of Coulomb force of attraction between these two is directly proportional to the charges Q1 and Q2, but that force is inversely proportional to the radius squared, distance between the two particles. Directly proportional to the charges, but inversely proportional to the distance. R means the distance. So here you see, if it is in first energy level, R will be short. I mean, the distance between these two is very small. But if you get it in third energy level, the distance is large. Then if distance increases, what about the force of attraction? It decreases. Distance increases, the force of attraction decreases, means the n equals 3 weakly bound to the nucleus compared to n equals 1 electron. Therefore, they ask this one. It takes more energy to ionize the electron from n equals 3 than from ground state. That's completely wrong. N equals 3 far away. less energy. Therefore, in question 1, part A should be false. It is false. The correct one is it takes more energy to remove electron from first energy level than the electron from third energy level. Correct, ne? Correct. B. The electron is further from the nucleus on average in n equals 3 state than in ground state. Of course, that's what I told you, me. The distance between the nucleus and first electron, first energy level electron, and the distance between the nucleus and third energy level, let's say r dash or something. This is r, this is r dash. As you can see, then r is shorter than r dash. Yeah, distance is large. Then B is true. Then what about C? The wavelength of light emitted if electron jump from third energy level to second energy level is shorter than the wavelength of light emitted if the electron falls from third energy level to first energy level. First transition given 3 to 2, third energy level to second energy level. Then, energy emitted E3 minus E1, because these are the two energies. Then energy of this electromagnetic radiation has energy E3 minus E1. Sorry. But then we compare the electron transition from n equals 3 to n equals 1. If it transmit from 3 to 1, what about the energy? Energy will be E3 minus E1. Then as you can see, the energy gap between 3 and 1 greater than the energy gap between 3 and 2. Because of that, here, the energy released larger. When the energy released larger, but the wavelength of this should be shorter. It should be shorter, like this. So as you can see now, the electromagnetic radiation that corresponding to the energy difference between 3 and 1, that is the energy released during transition of electron from 3 to 1, but that energy larger than the electron transition for 3 to 2. Energy increases, mean the wavelength of this electromagnetic radiation should be small, because you have learned these things. Energy is inversely proportional to the wavelength, right? So energy large mean the short wavelength should be there. So is that given here? C, I'm talking about wavelength of light if electron jump from 3 to 2. 3 to 2 means this one shorter than the, no, it's wrong. Because 3 to 2 small energy, then small energy mean lambda should be large. Therefore, this should be false. What about D then? The wavelength of light emitted when the electron returns to the ground state from 3 is the same as the wavelength of that absorbed to go from, of course. Then if electron returns from 3 to 1, the energy released will be E3 minus E1, energy released. But if it jumps from 1 to 3, a certain amount of energy absorbed, but that energy absorbed again, similar to E3 minus E1, same energy gap, similar to E3 minus E1. Got it? Therefore, if you consider same two electronic transitions, electronic energy levels, energy gap is same. Energy emitted or energy released during that electron transition should be same. So therefore, D, then C, D, same. The wavelength of light emitted, the electron return ground state, blah, blah. Energy same means the wavelength also same. So D, true. Then what about E? E given the first excited state corresponds to n equals 3. What is excited state? But before that, you need to understand ground state. Ground state is the most stable state. Most stable state means where the electron has the lowest energy. The electron has lowest energy when it is in the first energy level. Then ground state means any other state, because any other state should have higher energy level. Higher energies. Then if electron is in those energy levels, the energy of that electron is high, then it should be excited state. But then according to that, first excited state is not 3, even second energy level. You have electron in the second energy level. That electron has higher energy than the ground state. Therefore, second energy level should be the first excited state, not actually third energy level, n equals 3. So therefore, actually here A given later, but it should be E. So it should be false. It should be second energy level. So this is how we can understand the answers for the question number 1. Let's move to question number 2. Question number 2 is energy emitted or absorbed when the following electron transition occur from 4 to 2. From 4 to 2. Then if I go back to this one and then explain using the same diagram, this is the fourth energy level. N equals 4. Then electron transmit from 4 to 2. 4 to 2 means something like this. Where is it? I draw it here, 4 to 2. So when it comes from fourth energy level to second energy level, energy of electron decreases, means energy emitted. There's energy absorbed or emitted. So therefore, it should be definitely emitted. Then what about B? From the orbit of radius 2.12 angstrom to the radius of 8.46. Angstrom means the unit for the distance. Actually, 1 angstrom is equal to 1 into 10 to the power of minus 10 meter. So therefore, if you want to convert angstrom into meter, here there is no need to convert it because we can easily compare it. If it is 2.12 angstrom, 8.46 angstrom, then 2.12 should be definitely shorter. It should be closer to the nucleus. It should be closer to the nucleus. As example, let's say this distance R is 2.12 as example. It's not exact value. Then what about the R dash? R dash will be like 8.46 here. Got it? So then electron transmit from an orbit of radius this to this means then electron jump from first energy level to third energy level like that. Electron jump from first to third or first to fourth like that. I think you got the idea. This is not the exact distance. It's not the distance between the first energy level and the nucleus of hydrogen. As example, I got it. So if this distance 2.12, 8 means the larger than that, then it should be sometime second, third, fourth, fifth, can be like that. So therefore, electron transmit from lower energy level to higher energy level. If it transmit from lower to higher, definitely energy absorbed. You know, energy of electron increases, therefore, it should be absorbed. These questions quite easy, but these questions are arranged to make sure that you have understood the basic concepts in these electron transitions, energy levels, those things. Third question, indicate whether energy emitted or absorbed. Again, emitted, absorbed. When the following electron transition occur in hydrogen atom, from n equals 2 to n equals 6. Then again, n equals 2, starting from n equals 2 to n equals 6 means up. Lower to higher. Lower to higher means definitely energy of electron increases, means energy absorbed. Energy absorbed. B. From orbit radius 4.76 to 0.529. Then we start with 4.76, like somewhere here, 4.76. Then we come back to 0.54, means definitely it should be somewhere here. I just draw these things to understand it, Harry. Then it's 0.529. Then 0.529 should be shorter than 476. That means electron transmit from higher energy level to lower energy level. Outer energy level to inner energy level means higher energy level to lower energy level. Then what happened to electron energy? Definitely electron energy decreases. How? Released. So B should be then emitted, no release. This says energy emitted. Yes. Emitted. Next one, from n equals 6 to n equals 3. Again, 6 to 3 mean here going away from the nucleus to higher energy level. Definitely energy of electron increases. Therefore, it should be absorbed. Energy absorbed. Correct. Question number 4, there is some even calculation also. Therefore, better we have a new board. I'm going to erase this. Certain elements emit light of a specific wavelength when they are burned. Historically, chemists use such emission wavelength to determine whether specific elements were present in a sample. This is called flame test in inorganic chemistry. We will learn that one. You need to remember actually the colors. As example, sodium, yellow color. Likewise, you need to remember copper, green color, barium, light green color. So likewise. All right. Then here several elements given and wavelengths given, not the color. Characteristic wavelength for some of elements are given below. Determine which element emit radiation in the visible part of the spectrum. All right. I'm not going to explain the mechanism under flame test, but in that case also what happened, electron transitions. Once you have a certain element that has several energy levels like this, then during flame test what happened, electron transitions occur. First of all, here actually during that test what happened, we heat the sample. Once we heat the sample using the flame, energy supplied, the electrons in the low energy level absorb energy. If that electron absorb energy, it can't stay in the same energy level. You know that one. Energy of electron increases means definitely it moves to high energy level. We call it excitation. But again, excited state is not quite stable. Therefore, they try to come back. They try to reduce the energy of electron. When they come back, there are different electron transitions. Sometimes they come to first energy level, sometimes they come to only second, sometimes they come to second from third, like that. They have different electron transitions. Next thing, once you go from one element to the other, these energy gaps are not equal. These are different. That's why they give different colors to the flame. Okay. All right. That's the basic idea. But in inorganic chemistry, I will explain that one in detail with the videos and everything. All right. Determine which element emit radiation in the visible part of the spectrum. So as you know, then we can answer this question based on the theory we gain in unit 1. What is visible region boundary? 400 nanometer to 700 nanometer. That is where we have the visible region. Then any electromagnetic radiation having wavelength between these two values definitely lies in visible region. All right. Which element emits? What about silver? 300. No. Orus, gold, 200. No. Barium, 455. Barium definitely should be within this one, 455. Barium. Next, calcium, of course, 422. Next one, copper, 324. Copper, 324, it is outside. But, you know, the thing is this one, this is the range it's given. According to that range and the given wavelength here, 324, copper cannot then impart the color to the flame here. But once you do the experiment, you will see copper also gives green color flame. But according to these values and these boundaries, I just ignore copper. 372 can't be. Then 404 potassium, yes, can be. 404 within this, then definitely it can be. Magnesium 285 cannot be. Sodium, of course, it is within this. What else? Nickel, no, it can't be. 341. Yeah, these are the elements that are found within the visible region. Then these are the elements that can give some colors to the flame. Which element emits photon of highest energy and lowest energy? They ask about highest energy, lowest energy. But what is the data available? Wavelength. But we know this one, energy is inversely proportional to wavelength. That's what available. Lambda available. Question is about energy. Then we need a relationship between lambda and energy. They ask highest and lowest. Then based on lambdas, we can find it. Then, highest lambda, longest one, should have the lowest energy. Then shortest lambda should have the highest energy. So which one out of this? I'm talking about the highest one. Then highest one, I think sodium, 500. Yeah, it should be sodium. They ask first highest energy. They ask highest energy first. Okay. Highest energy is found in the shortest wavelength. Shortest means 285. 267 also there in Horus. Anything else? No. Horus, AU. AU has the shortest wavelength, means it has the highest energy. Then what about the lowest? Lowest should be found in sodium. Lowest energy I'm talking about. Lowest energy sodium because it has the longest wavelength 589. Quite easy. When burned, a sample of unknown substance is found to emit light of frequency. This. Which of these element is probably in the sample? Then you are given the frequency of this unknown element, but you are asked to find out which element is that. Then, then using frequencies we can't find because the data are given for lambdas. Then you have to find out the lambda here. You know the relationship between frequency and lambda. Lambda equals C over mu. C constant 3, 8, 10 to the power of 3 into 10 to the power of 8 meter per second, and mu given like 6.59 into 10 to the power of 14 10 to the power of 14 per second. The per second cancel, then we get answer like 10 to the power of 8 and 14 cancel, then 6 remains. 10 to the power of 6 comes up, it becomes minus 6 into, then we have to find out this one, 3 divided by 6.59. Let's go for a exact value. 0.4552 0.4552 like that, but it's given in nanometer. Nano mean 10 to the power of minus 3. How can I make minus 9? Nano means 10 to the power of minus 9. This is in meter. How can I make the minus 9 part? Then better you take a 3 decimal place forward and then put it like 10 to the power of minus 3. Is that clear? 0.4552 can be written like 455.2 into 10 to the power of minus 3. Then 10 to the power of minus 6 also available. Then 455.2, this whole part 10 to the power of minus 9 can be replaced with nano. In unit 3, next, within this month, we are going to start, maybe next week or the following week, we are going to start unit 3 chemical calculation. In calculation, I will explain some easy method to do these type of conversions. 455 nanometer, then which can be the element here? 455 definitely should be within visible region. It should be barium, calcium, potassium, sodium. Barium, calcium, barium 455. Exactly, it is barium. 455.2, 455.4 given. Yeah, your answer should be barium. Part C answer is barium. Correct? So if you have still some doubt regarding this one, better you contact with me through WhatsApp, then I can clear it further. But this explanation, I hope it's enough to understand the mistake. Consider the following approximate visible light of spectrum. Hari, wavelength given, colors are given. Barium emits lights in the visible region of the spectrum. If each photon of light emitted from the barium has an energy, which color of visible light is? Actually, we know now already barium is green because these things we already discussed, but let's see whether it is green. By calculation, we have to prove it. But in this case, what is given? Lambda available in centimeters, but energy is given. Then you need a relationship between wavelength and energy. Then using energy given, you can find the wavelength like this. H is 6.63 10 to the power of minus 34 joule second. C 310 to the power of 8 meter per second. Then energy given 3.59 10 to the power of minus 19 joule. Minus 19 joule. Correct. As I advised in the class, first simplify the the units. Joule cancel, second per second cancel. We end up with meter. Then simplify the 10 to the powers. Then 10 to the power of minus 19. Here minus 15. 10 to the power of 8 minus 15, it's minus 7. 10 to the power of minus 7. Right. Then you have 6.63 into 5.54. 5.540. We get 5.540. That's what we get. 5.540, 10 to the power of minus 7. But what you are given in the wavelength are given in centimeter. Ne? Centimeter, what is it? Centimeter 10 to the power of minus 2. Ne? Right. Then I write it like this. 5.54 into 10 to the power of minus 5. I take minus 5 out into 10 to the power of minus 2 meter. Did I do any mistake here? No. I just break down 10 to the power of minus 7 into minus 5 and minus 2. It's possible in the case of powers. You know what to happen. Addition and give minus 7. But again, I write it like 5.54 10 to the power of minus 5. But minus 2 replace with centi. Minus 2 replace with centi. So lambda in centimeter, 5.54 10 to the power of minus 5. Yes, where is it now? 5.54 10 to the power of minus 5. When you look at the diagram, clearly it should be green given 5, middle green given 5 into 10 to the power of minus 5. Then when you get 5.5, then 5, the orange 6, then between 5 and 6, the middle becomes somewhere around yellow. According to the calculations and the given diagram, you see 5 here in the case of green, 6 here in the case of orange. Between 5 and 6, exact middle is definitely lies somewhere in yellow color. So according to the values given and according to the diagram given, the color should be yellow. But actually, when you do barium, that flame test, it gives actually green color, apple green like that. But here we follow the data given and the diagram given. Then according to that, it should be somewhere yellow, 5.54 10 to the power of minus 5. Yeah. Okay, that's the best position. Sometime I will simply edit this video to make the time small. Therefore, all the parts will not be available. Sometimes you see the board full of letters, numbers, but suddenly it disappears. It's not, you know what happened then? I erased the board and I cut that part from the video. It is not some superpower or something. Sixth one. A certain quantum mechanical system has energy level shown in the diagram. The energy levels are indexed by single quantum numbers. N is an integer, okay? 1, 2, 3, 4, 5, like that. As drawn, which quantum number are involved in the transition that requires the most energy? Now, we are going to use the given diagram. Sixth one, the diagram given like this. Here n equals 4. You see n equals 3. Now gap increases. It's okay. We refer the given one. This is 1, 2, 3, and 4. These are the energy level. As drawn, which quantum numbers are involved in the transition that requires the most energy? The most energy electron transition, we have to find out the largest gap. Largest gap means the lowest energy level and the highest energy level. That is where you get the largest gap. So therefore, during electron transition from 1 to 7, that is where you get the most, as you can see. Then, part A, the answer should be n equals 1 to n equals 4. Which quantum numbers are involved in the transition that requires the least energy? Then here opposite mean least energy mean the smallest gap. I mean, 2 consecutive energy level which has the small gap, but it's not 3, 4 because gap large. It's not 2, 3. It's again a gap larger than this. It should be 1, 2. This is where you get the shortest gap. Then n equals 1 to n equals 2. We refer the diagram and then give the answers, not what you know. I mean, in the case of hydrogen emission spectrum, we discuss hydrogen energy level not like this. When you go away from the nucleus, energy gap decreases. But here it's given energy gap increases, but it's okay. We refer what is given. Based on drawing, put the following in order of increase in wavelength of the light absorbed or emit during the transition. Actually, from the diagram, we can identify the energy variation. Which one is lowest energy, which one is highest energy gap. But they asked to arrange them according to increase in order of wavelength. But then we know the relationship between wavelength and the energy. Energy is inverse, wavelength is inversely proportional to energy. Wavelength inversely proportional to the energy. Then look at this. 1, 2. 1, 2, smallest energy. The smallest energy mean it should be the longest wavelength. First one, I just put the number. That should be the longest one. Thereafter, 3, 2. 3, 2 means this one, quite small but large compared to this. Next, 2, 4. 2, 4 mean this size. Okay, I'll come. Then 3 and 1. 3 and 1, this one. Okay, let's draw it. Next, 3, 2. 3, 2 means this one. 3 to 2, this one. Hurry. Next one, 2 to 4. 2 to 4 is this one. Hurry. Next one, 3 to 1. 3 to 1 is this one. Hurry. Then tell me which one is next. I mean, the smallest gap is found here. According to the given 1 to 1 to smallest. 1 to smallest. This one is not there. 1 to 4 is not there. Yeah, 1 to 4 is not there. Just erase that one. These are the 4 transitions given. The largest gap is found 2 to 4. 2 to 4, that is where you get the smallest wavelength or shortest wavelength. Where is given 2 to 4? 2 to 4 given in third. Therefore, third one should be, that is where you get the shortest one. Now the question is 2 and 4. Out of 2 and 4, 2 given 3 to 2. 3 to 2, this one. 4 given 2 to 4. 2 to 4, this one. Definitely 3 to 2 shorter, I mean the small energy. 3 to 2 small energy mean 3 to 2 should have then longer wavelength. 3 to 2 means it's second one. Then second one should be longer than fourth one. Got it? What is first one? First one is this small one. What is second? Third one? Third one is this largest one. Then what is second one? Second one is this one, this transition. And what is fourth one? Fourth one is this transition. These are the transitions given. According to that, we can identify. The basic idea is this one. Gap small, small energy. The other thing is this one. Small energy mean longer wavelength. That's what they check. In question number 7, emission spectrum of hydrogen consists of several series of line. You know, Lyman, Balmer, Paschen, Brackett, Funds. These series of highest energy is called Lyman series. Yes, the highest energy we call it Lyman series. Highest is called Lyman series. Yes, in that case, electron transmit from higher energy level up to the first energy level. That's why the gap is largest. Each line in the series is results in electron transition, blah, blah, given. Hurry. State in which direction. Okay, then this is again a basic thing. I don't draw everything, but if I draw something, A line here, B line here, and C line here. So what happened to energy? I mean, the gap between two energy levels. I mean, the two lines, gap between two lines decreases. In the if you remember hydrogen emission spectrum, to the direction where the gap between two energy level decreases, the energy represented by line increases. Therefore, gap decreases mean energy represented by line should increase. Then energy increase from A to C. But here, final thing given, not C, G. They have used G. Then what's the first thing? First thing is direction energy increases. A to G or G to A. It should be A to G. In spectrum, find out to which direction the gap between two lines decreases. That is where the energy represented by line increases. Got it? I don't have to draw it. Maybe you remember that one in hydrogen emission spectrum. I explain it in detail. Just take Lyman series like that. This is what I got actually. I think for Lyman, then 2 to 1 transition, this line represent. Once electron transmit transition from 2 to 1, energy E2 minus E1, that energy represented by this line. Right? Then 3 to 1. Energy now E3 minus E1, that is larger than this. Energy large, then that line should represent large energy. Then I place it somewhere here. or it can be here, doesn't matter. You can select to which direction energy increases. It is your option, right? So you can select the direction to which the energy increases. I selected to this side. I mean, right to left energy increases. Therefore, this line should represent more energy because gap large. Then this represent more energy than this line. Next thing, 3 to 1, either 4 to 1. 4 to 1 emits more energy, gap larger than the previous, more energy, E4 minus E1. Then I should place that line definitely in the left hand side. But I think you remember, I kept these gap decreasing to that direction. Why? Because this gap represents the energy difference between these two energy levels, 2 and 3. Right? So let's say A or something. This is A. But what about this gap? It should represent energy difference between 3 and 4. Energy gap between 3 and 4 should be smaller than the energy gap between 2 and 3 according to both theory. The gap between second and third line of Lyman should be smaller than the gap between first and second line of Lyman. You need to understand this logically. Look at this. Then to this side, left to right here, gap decreases. Gap between two line decreases. The gap decreases, but energy represented by line increases. That's what I say. Here in the given diagram, from left to right, the gap between two consecutive line decreases. Then to that direction, the energy represented by line should increase. Therefore, energy increase from A to G. State in which direction the frequency increases. Then energy and frequency directly proportional. Energy directly proportional to frequency. Then it should be same direction. C. Explain why the spectrum consists of line. Then why it is line spectrum, not continuous. Continuous means there is no any gap here, missing part. All the electromagnetic radiations available there. You remember that I showed you the pictures and everything. In that case, in emission spectrum, complete color band is there. There is no any missing lines there. But here, line spectrum. Why? The reason is, during this experiment, hydrogen emits energy only at specific wavelengths. During this experiment, hydrogen emits energy only at specific wavelength. It does not emit all the energies. It emits energy only at a specific wavelength. So that is why at those points you have line. That is enough. I mean, during this experiment, hydrogen emits energy only at specific wavelength. That's enough. What do transitions in the same series all have common? I mean, as example, here you have to say only at a specific wavelength. Let's put lambda. Energy emits only at specific wavelength. For a given series, then what is the common thing? I mean, if I say Lyman, which one is common? Energy same? No. Energy different. Frequency same? No, difference. Wavelength same? No, difference. What's the common thing here? Common thing is this one. If it is Lyman, I told you, electrons transmit from high energy level to the first energy level. That's the common thing. All transitions in Lyman end up with the first energy level. All the transition in Balmer end up at then second energy level. So therefore, that's the thing. All electron transitions end at the same energy state. That is enough. Okay. All the transition end at the same energy level or same energy, electronic energy level, same energy level. That's how we answer the question for 8th one. Hari, what about the 7th one? 8th one is, that is ionization energy part. Up to this then spectrum. Now you have a question based on ionization energy. Question number 8, the successive ionization energies for an unknown element given. Hari, successive ionization energy. 1, 2, 3, 4, like that. Hari, to which family in the periodic table does the unknown element most likely to belong? Actually, using the values, it's sometimes quite difficult to analyze this. So my advice is then, if you are given this type of thing, better you have a rough diagram. This says ionization energy in kilojoules per mole. This has removal of electrons. We discussed this type of diagrams or the graphs, and we did several questions to practice this graph and everything. You remember that? 890, 1007, 14,000, 17. That's how you have it. I take like this one 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, like that. So this is 1000. But first one 896 mean first ionization energy should be somewhere here. Second 1007, it should be between 1 and 2, 1000, 2000. Third one, very fine, third one. Yeah, third ionization energy is given 14,000. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. 14,800 mean nearly 15,000. It's somewhere here. Thereafter 17, 15, 16, 17. 17 somewhere here. Can you see that diagram? It's like this. This is the diagram which represents successive ionization energy, but there are only four successive ionization energies given. Then they ask to which group the periodic table, to which family means the group. Then it is easy to understand. I told you, go to the bottom part and then see how many electrons are there, how many electrons are there in the bottom part. In that case, it's clear these electrons require lowest energy. Those electrons requires lowest energy. That's because those electrons are in the outermost energy level. Because if electrons are in outermost energy level, the attraction between the electron and nucleus is weakest. The weakest attraction requires the lowest energy. You know those points. Therefore, these are actually the electrons available in the outermost energy level. There is another name for outermost energy level. We call it valence shell. Therefore, what is this actually represent? It gives the number of valence electrons. Number of valence electrons, the below part, valence electrons. Then how many valence electrons are there? There are 2 valence electrons. Then I told you, number of valence electrons give the group number of this element in the periodic table. So using this graph, actually, we can get some information. Group number can be identified, even period number can be identified. Here we can't identify period number because we don't know whether it has 4 electrons. In the class, I explained how to identify the period number. Here question is which family mean group. Then valence electrons 2, then what should be group number? Group number 2, group 2. Someone can say group 2, or someone can say in periodic table, I gave a specific name for group 2 elements. What is it? Alkaline earth metal. So therefore, this element should be an alkaline earth metal. Ninth question, again, based on that type of graph. Ninth question is there. That also has this type of graph. Okay. So this is ionization. This is removal of electron. I don't label them. First one here. Second one here, according to the graph. Third one here. And which one is then fourth one. Fourth one has the higher value, and fifth one larger than fourth one, but no large gap. This is how you are given. Then same story. Go to the bottom part of the graph and identify how many electrons require lowest energy. According to this graph, only 3 electrons requires lowest energy. Then if 3 electrons require lowest energy, it should be group number 3, but the valence electrons 3, number of valence electrons 3, then group number 3. But here we take the group number like 13, because this pattern is not found in the case of D block. Group 3 is D block element. Group 3 to group 12, it's D block. But in the case of trends of this ionization energy and everything, we got S block and P block only. We ignore D block. Why? It has certain variation, but it is irregular variation. We'll come to that one under D block, inorganic chemistry. Right? So therefore, remember that one. 1, 2 belong to S block. After that, next one group, we go to group 13, P block. We omit that D block part. 3 to 12, we omit. Therefore, if there are 3 electrons, it's not group 3, it should be group 13. This is group 13 element. Is that they ask? Which group of the periodic table does S belong? Oh, yes. Then it should be group 13. What is next question? B. If the atomic number exceeds Z, then plot the graph of first 6 ionization energies against the number of electrons removed in of the element having the atomic number Z plus 1. Group 13. Group 13, what are the elements? Boron, aluminium, gallium, indium, thallium. Right? Now, let's keep it like aluminium or something as example. If the atomic number is Z, actually aluminium 13. Now they ask atomic number Z plus 1. If Z is 13, Z plus 1 is 14. What is 14? It's silicon. Z plus 1 means 14. Silicon. They ask about silicon. Or they ask about carbon. Or they ask about germanium. So likewise, just I consider aluminium third period and then try to explain this. Then now, silicon is the question. They asked to draw it first. 6 successive ionization energies of this 1, 2, 3, 4, 5, 6. Then look at this group 14. Group 14, what about the number of valence electron? 4. Then that means up to 4 electrons, up to 4th energy level, the gap increases, but it's not then significant gap. Between 4 and 5, there should be a significant gap. That's the rule. Then you can get it like that. But this way, if you draw it, it's okay. Right? It goes like this and then increase and like this. That is acceptable. First 4 have then low energy. It is at the bottom part. But there should be a significant gap between 4 and 5. That's what they will check. But since now you know electron configuration, stability part and everything, now we can further explain this part without giving a straight line. How can I explain? I took silicon group 14, 1s2, atomic number 14, 2s2, 2p6, 3s2, 3p, 2 electron configuration. Once you remove the first electron, you remove electron from 3p2. Once you remove electron from, the second electron, it's from 3p1. Third electron is removed from 3s2. You know, then removing electron from 3s2 will be quite difficult. Why? Because it has a complete stabilization. Then the gap between first and second, if you keep it this much, the gap between second, third will be quite large. It's not significant like this one, but compared to this gap, this should have quite high gap. Why? You know the reason? Because third electron removed from a stable configuration. Thereafter, you remove electron, fourth electron from 3s1. Therefore, it increases because nuclear attraction per electron increase, size of energy, electron cloud decrease. Because of that, it increases, but no, like this gap. Sorry. Therefore, this gap, there should be a quite large one compared to the other gaps. So if you draw it in this manner, that will be then highly accurate. But the largest gap is there in between 4 and 5. This could be answer. If you have given these 4 straight line, still it is correct. But I think now you know something more than that. Quantum number. Which of the following set quantum number are not allowed in the hydrogen atom? For the set of quantum numbers, that is incorrect state, what is wrong within each set. To select this one, which one correct, which one not correct, but we need some kind of rules. N, there is no rules. Integer 1, 2, 3, 4 like that. But for L, there is a rule. What is it? it should be starting from 0, but continue up to n minus 1 only. You can't pass that. In the case of ml, there is a rule. You can start from only from minus L. You go through 0 and come up to plus L. In ms, there is a rule. Just two values are possible, plus half O minus half. Then if there is any electron configuration, or combination, quantum number combination where one of this violated, then it is incorrect. That's the thing. Hari, what about A? A, it's given n equals 3, L equals 2, ml 2. Is in 1 given? No. In 2 given? Yeah. Then n equals 2. L according to that 0, 1, 2 possible. 0 up to n minus 1. 0 mean it's 0 here. This can be plus half or minus half. If L equals 2, it's minus 1, 0, plus 1. Here plus half, minus half. In 3 available, according to that 0, 1, 2. N minus 1, 2. This has 0, minus 1, 0, 1, minus 2, minus 1, 0, 1, 2. These are the possibilities. N equals 3, not 2. Then n equals even 4 available. If it is 4, it should be 0, 1, 2, 3 possible, up to n minus 1, 4 minus 1, 3. This can have 0, minus 1, 0, 1, minus 2, minus 1, 0, 1, 2, minus 3, minus 2, minus 1, 0, 1, 2, 3. These are the things. Then go to the first one. 3, 2, 2. Is that 3, 2, 2? Yeah, possible. No problem. A correct. A correct. A is correct. B given 4, 3, 4. 4, 3, 4. There is no 4. Therefore, this is incorrect. What's the problem? ML should be in between minus 3 to plus 3. Then 4 outside, so it can't be. B correct, incorrect. C, n 0. There is no 0. N should start from 1. That's the minimum one. Can't be 0. N equals 0, not possible. N equals 1. So C, n should start from 1. It can be 1, 2, 3, 4, like that, not 0. D, 2, minus 1, 1, 2, 2. Then L minus 1. L minus 1 can't be. If n equals 2, the possible L values 0 and 1 only. There is no minus 1. Therefore, D also wrong. C wrong and D also wrong. N should be 0 and 1 only, not minus 1. Okay, that question, then just check the basic one. Question number 11. Let's go to 11th one. I think this will be helpful, therefore I don't erase it. 11th one. What's question? Which of the following set of quantum numbers are again allowed, not allowed? Each is incorrect state. State why it is incorrect. The rules, actually. What are the rules? First one. 3, 3, 0 minus half. 3, 3 not possible. If n equals 3, L equals not 3 possible. In this case, it's wrong because L can be 0, 1, 2 only. B, 4, 3, 2 minus half. 4, 3, 2 minus half. Yeah, it is possible. B, no issue. What about C? 4, 1, 1 plus half. 4, 1, 1 plus half. Yes, that's also correct. D, what I said here, you remember, then D wrong. Why D wrong? 11th one, D. Why D wrong? D. The problem is MS minus 1. It's not possible. MS could be plus half or minus half. Then what about E? N5 L minus 4. N5 L minus 4 not possible. If I draw it here, I think you can see it. If N equals 5, what are L value? I write it like this. 0 possible, 1 possible, 2 possible, 3 possible, 4 possible, up to N minus 1. 4 possible. But here it's given minus 4. Minus 4 not possible. So therefore E wrong. What are possible L values? 0, 1, 0, 1, 2, 3, 4, plus 4, not minus 4. If 3, 1, 2, 3, 1, 2 not possible, 3, 1, 2 not possible, it should be from minus 1 to, therefore that's wrong. Then ml can be minus 1, 0, 1 only. 3, 1, 2 not possible, therefore F wrong. So 11th one, we can answer it in this manner. Got it? See, these questions have been arranged to check whether you have understood the concept properly. Because understanding the concept will solve the 50% of your exam question. Other 50% will be the memorizing part and experience of analyzing the questions. Maybe it depends on the maths skill, logical thinking. Those are the things. But 50% is just understanding the concepts in the classroom. So these questions develop, they're given for that one to check whether you understood it. But now you further understand it once we have this type of discussion. 11th one, then I erase it and go to 12th one. I hope this will be helpful for 12th one. What is 12th one? What is the maximum number of electrons in an atom that can have these quantum numbers? Sorry. 12th one I'm talking about. N equals 4. First A, N equals 4. What is the maximum number of electrons? You see, if N equals 4, these are the sub-energy levels. There are 4 sub-energy levels. There are how many? 17. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. 4 means 16. 16 orbitals are available. There are how many ms values are there? For each and every orbital, there are 2 spin quantum numbers. Mean there are 2 electrons. There is 16 into 2, 32. Oh, there is another short method I gave you. If n is the principal quantum number, the maximum number of electrons given by 2n square. We learn it in the classroom. So n equals 4 means 16 and there are 32. 32 electrons can have n equals 4. B, n equals 5 ml plus 1. N equals 5 ml plus 1. Then I should draw it because here n equals 5 not there. Then look at this, n equals 5. Then what I'll value? 0, 1, 2, 3, 4. Then they check ml. Then ml, here 0, 1, 0. Is it given plus 1 or what is it? Yeah, plus 1 given. Okay, let's plus 1. This is minus 2, minus 1, 0, plus 1, plus 2. This is minus 3, minus 2, minus 1, 0, plus 1, plus 2, plus 3. This is minus 4, minus 3, minus 2, minus 1, 0, plus 1, plus 2, plus 3, plus 4. These are possible sub-energy levels. Then they have given the condition only for n equals 5. This condition given, it can be any possible L value. L not mentioned mean it can be any L possible L value. But ML given, ML can be plus 1 only. Then these things only. Can you see that one? Is this possible? Yes, possible. ML1, n equals 5. L1 doesn't matter. They have not given the L. Is this possible? Yes. Why? ML plus 1 in 5. L2 doesn't matter. Is this possible? Yes. ML plus 1 in 5. ML plus 1 in 5. Therefore, these 4 are possible. What are ML? ML represent orbital. 1 ML value represent 1 orbital. Look at how many orbitals are there? How many ML's value are there? 1, 2, 3, 4. Then how many orbitals? 4. But they ask not the orbital, but the electron. They ask maximum number of electrons. Then if there are 4 orbitals, 1 orbital 2, 2 into 4, there can be 8 maximum electrons for a given atom, which has n equals 5, m equals plus 1. Then 8 electrons can have this n equals 5 and ml plus 1. That's the meaning. Got it? C. Let's go to C. So what is C? N equals 5, ml, ms plus half. N equals 5. Then this one. N equals 5. There is no condition for L can be any value. There is no condition for ML can be any value, but there is MS plus half on. Then you know, for fifth energy level, if you apply this rule, there are 50 electrons, 50 electrons total. But out of 50, half of that, 25, should have plus half MS. Other half, 25, should have minus half. Therefore, n equals 5 plus half only, then it's definitely 25. I hope you understood it. They have not given n L value. Then it can be all the 5 values possible. ML, then all the 25 values possible. Okay. But in MS, it can't be all the 50 values because only plus half. Then half of that, it should be 25. D. 12th question, D, n equals 3, L equals 2. N equals 3. Then it's given like this way, n equals 3, L equals 2. Means it's 3D. How many possible electrons? How many electrons can have n equals 3 and L equals 2? No condition for ML. It can be any value. Mean 1, 2, 3, 4, 5. 5 values are there. 5 orbitals are there. Then how many MS values? 5 into 2, there are 10. Therefore, n equals 3, L equals 2. 10 electrons can have those two combination, those two quantum numbers. Hurry. Let's go to E. That is D. Then this is E. Next one, E. E, n equals 2, L equals 1. N equals 2, L equals 1. It is about this one, 2 and 1. Then same thing actually. Once I come to this, then these two condition, but here no condition. Means there are 3 possible ML, 3 orbitals. 3 into 2, there are 6 electrons inside this 2 and 1. There are 6 electrons. So E, the answer should be 6. F. N0, L0, ML0. What is that? It's 0. Right? What is the maximum number of N0? Then there is no any electron in an atom can have N equals 0. So 0. G given N2, L1, ML minus 1, and even MS, this can have 2 plus half O, minus half only 2. But here again minus half given. Then definitely, then how many? All the 4 quantum numbers given means definitely 1 electron. Just 1 electron. There are 2 here, but now minus half represented, I mean, they're specified. Therefore, only 1 electron can have that combination. G, then 1. Okay, G1. Thereafter, H given n equals 3. Hurry. Now n equals 3 given. N equals 3 means this one. Hurry. N equals 3. Where is it? H. Oh. There is no condition for L. L can be any values. Hurry. There is no condition for ML. ML can be any value. Right. But there is a condition for then. Okay. Then it is easy. Because all are possible, right? All are possible. Then how many electrons here total? There are 1, 2, 3, 4, 5, 6, 7, 8, 9 orbital. 9 into 2, there are 18 electrons. Total 18 electrons for n equals 3. But they asked us to find out only plus half spin quantum number. For 18, there are 2 plus half minus half. But plus half only mean half of that. It should be 9. 18 divided by 9. 18 divided by 2. It's 9. 9 electron only can have these combinations. Sorry. A, B, C, D, E, F, G, H. We go to H also. Hurry. Then I. This is I. Yeah, I. N equals 2, L equals 2. N equals 2, L equals 2. We don't have that. There is no any electron can have N equals 2, L equals 2 because there is no such combination. If N equals 2, possible L 0, 1 only. J, N equals 1, L equals 0, ML 0. J. n equals 1, Hari, L equals 0, Hari, and ML equals 0. Then these three. Here, there are two possible plus half, minus half. Means two electrons are having these combinations 1, 0, 0. 1, 0, 0 can have 2. 1, 0, 0 minus half, 1, 0, 0 plus half. Two electron can have 1, 0, 0. That's how we get the answers for question number 12. Question number 13. For n equals 4, what are the possible value of L? For n equals 4, what are the possible value for L? Easy. N equals 4, what are the possible value for, what are the possible values of L? 0, 1, 2, 3. 0, 1, 2, 3. B for L equals 2, what are the possible M? For L equals 2, this one, what are the possible ML or L? Yeah, it is minus 2, minus 1, 0, 1, plus 1, plus 2. You see, these are easy questions, but that too, I told you the purpose of giving this question. Hurry. If ML2, what are the possible L? If ML2, what are the possible value of for L? If ML is 2, what are the possible value of L? ML2, the possible value 2. If ML2, the possible value can be L can be 3. Then 4, 5, 6. Then we can say any L value higher than 2. L can be then 2, 3, 4, 5, etc. In all these cases, there is ML2. You got it, ne? L0, there is no ML2. L1, there is no ML2. But L2, there is ML2. L3, there is ML2. Likewise, L2, 3, 4, 5, 6, anywhere you can find ML2. They are what are the possible values for L, but there is no limit here. Can be like this. 14th, give the values for NL and ML4. Give the values for NL and ML for each orbital in the 2p subshell. Where is 2p subshell? 2p means the main energy level, second energy level. P means L equals 1. So this is 2p. This is 2p, but they ask what? Give the values for, I'm talking about 14. Give the values for NL, ML for each orbital in 2p subshell. L can be 2. L should be 1. Then each 2p, ML can be minus 1, 0, plus 1. This can be 2px, this can be 2py, this can be 2pz. They ask each 2p orbital. 2p can have 3 orbital, 2px, 2py, 2pz. Then they ask to write NLM. For 2px, what is it? 2, 1, minus 1. 2py, 2, 1, 0. There is no like that. I mean, 2, 1, 0 can be 2px also. Anyone can get like that. Then simplify, write it 2, 1, 2, 1, 0, 2, 1, minus 1, 2, 1, plus 1. These are the NLML values. This is NLML values for each orbital in 2p subshell is like this. This is part A. What is part B? They ask each orbital in a 5D subshell. Each orbital in 5D. But in that case, 5D mean like this, 5, n equals 5. D means what is else? L1 P, L2 should be D. 5 D mean L2. Then ML values, minus 2, minus 1, 0, plus 1, plus 2. Then how many d orbitals? There are 5. Okay, then it can be like 5, 2, minus 2. Other 5, 2, minus 1. Other 5, 2, 0. Likewise, other 5, 2, 1. Other 5, 2, 2. These are NL, ML values for all the d orbital available in 5D. Let's go to question number 15 and try to understand this. Question number 15. For the table that follows, write which orbital goes with quantum numbers. Right, which orbital goes with quantum numbers. Don't worry about XYZ subscript, okay? If the quantum numbers are not allowed, write not allowed. Hurry. Then these are the things given. N equals 2, L equals 1, ML equals -1. Hurry. This one 1, 0, 0. This one 3, -3, 2. This one 3, 2, -2. This one 2, 0, -1. This one 0, 0, 0. This one 4, 2, 1. This one 5, 3, 0. These are the combinations given, but they ask us to write the one example given. Then 2p. Second main energy level, L1 mean P sub energy level, so it's 2p. That's what you have to write. 1, 0, 0. 1, 0, 0 possible, and 1, 0, 0, 1 first main energy level, L0 mean S. This is about 1 S. 3 minus 3 minus 3, 2. 3 minus 3. Can we see 3 minus 3? No, 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 no. Then here you are asked to write not allowed. This is not allowed. 3, 2 minus 2. 3, 2 minus 2. Yes, yes, it is allowed. 3, 2. SPD. 3, 2. 3D. Next, 2, 0 minus 1. 2, 0, 0 possible, but -1 not possible. 2, 0, 2, 0, -1 not possible. Therefore, here also we write not allowed. It's not allowed. Next, 0, 0, 0. Is it allowed? There is no 0, 0, 0. Not allowed. Next, 4, 2, 1. 4, 2, 1. Possible. 4, 2, 1. First of all, you have to check whether it is allowed or not allowed. It is allowed. Then 4, 2. L equals 2 is for what? D. So this is fourth main energy level, D sub energy. 4D. Next, 5, 3. 5, 3 possible because up to n minus 1, up to 4, it's possible. And 3, all the value from -3 plus 3, yes, 0 possible. But 3 is what? F. F. Therefore, this should be 5F. Those are the answers for question number 50. Question number 16 next. In the case of 16, what do we have? First part. What is the maximum number of electrons that can occupy each of the following subshells? It is easy again. We know how to answer 3p. They ask maximum number of electrons. So 3p means this one. In that case, there are 3 orbitals. 3 orbitals. 1 orbital maximum 2. 3 means 6. Next, B, it's 5D. 5D. 5D means 5D D here. There are 5D mean 5, 2. 2 means 2 can have -2, -1, 0, +1. There are 5 orbitals. 5 orbitals mean maximum 10 electrons. They are electrons, net orbital. Maximum number of electrons, yes. C, 2s. 2s, then it's 2 and s. It has only 1 orbital. 1 orbital can have maximum 2. D, 4f. 4f means 3. 4, 3. And then there are 1, 2, 3, 4, 5, 6, 7 orbitals. 7 orbital mean 14 electrons. 16, second part, they ask, what is the maximum number of electrons in an atom that can have the following quantum numbers? N equals to ms minus half. N equals to, no condition for L, anything possible. No condition for ml, anything possible. but ms only minus half. Then you know how to do. N equals to, yes, there are 1, 2, 3, 4 orbitals. 4 orbitals can have 8 electrons, but all 8 electrons can have minus half plus half, but they are minus half only. Then 8 divided by 2, 4 electrons only. 4 electrons only can have N equals to ms minus half quantum number combination. B, N equals 5, L equals 3, N5, L3. L3 means there are 7 ml values, minus 3, minus 2, 0, like that. 7 ml values mean 7 into 2. 14 electrons can have 5. N equals 5, L equals 3. C, N4, L3, N4, L3, hurry, ml minus 3. Then they have given a condition. It's only this one. 4, 3, minus 3. So one orbital, they represent one orbital. One orbital can have maximum 2. Then 2 electrons can have N4, L3, ml minus 3 quantum number combination. Last one, D, N400, 400, 400. All the three specified mean one orbital. One orbital means only 2 electrons. Correct? Right. Now they have combined the quantum number and the electron configurations. Let's see how to answer those type of questions. Question number 17. Nickel in ground state of nickel. First, you need atomic number for nickel to write the configuration. It's 28. To answer this type of questions, it will be good if you write the complete electron configuration, not the electron condensed one. Like we wrote the electron configuration using inert gas core. But they asked the question, how many electrons occupy atomic orbital in equals 3? How many electrons occupy D, P, Z, like that? Then better to answer these type of question, we write the complete electron configuration. Then 28 mean 1s2, 2s2, 2p6, 3s2, 3p6, thereafter 4s2, and then 3d8. Total, there should be 28 electrons for nickel. Hurry. How many electrons occupy atomic orbital N equals 3? This is N equals 3, N equals 3, N equals 3. Then how many electrons? 2, 6, 8, 8 plus 8, 16. 16 electrons are there, N equals 3. Third energy level, N equals 3, has 3 sub-energy level, SPD. We find 2 in S, 6 in P, and only 8 in D, not completely filled. B, how many electrons occupy D atomic orbitals? How many electrons occupy then SSP, SSP, SP, S, and D. In D, you can have only 8 electrons. Is it nickel or nickel? Oh, yeah, just nickel. Not iron given. Sometimes they may give nickel 2 plus, then we have to remove 2 electrons. But here, just nickel given, ground state. How many electrons occupy Pz atomic orbitals? Then you know, once I consider 2p, there are 3, 2px, 2py, 2pz. Once I consider 3p, there are 3, 3px, 3py, and 3pz. In 4, there is no 4p. Now they ask only z, 2p, 2pz or 3pz. They ask just pz. Pz can be then 2pz, 3pz. Then there are total 6 electrons. You know how we fill these things. Single electrons like this. Thereafter paired. Then, here 3p6 completely filled. Then 1, 2, 3, 4, 5, 6 like that. Then in 2pz there are 2. 3pz there are 2. Total there are 4 electrons. You can find 4 electrons in pz atomic orbitals. Then once you understand the concept, that those questions are very easy. 18. Write the expected ground state electron configuration for the following. The element with one unpaired 5p electron that forms a covalent compound with fluorine. In that case, then we need some idea about the covalent bonding. We can have sometime covalent bond between two atoms. We can have sometime ionic bond between two atoms. Then how to differentiate it? It's based on the electronegativity differences. Right? In bonding, we will discuss once we started bonding and we have completed a covalent also. But once I go to ionic, I'll compare ionic covalent and explain you how to decide it is covalent or ionic. There is a certain electronegativity difference. Above that, ionic, below that, covalent, like that. We'll come to that later. Anyway, the element with one unpaired 5p electron, that forms covalent. Now, when generally, logically, we can have like that. 5p, one unpaired means, 5p1. 5p1 has only one unpaired. But what about 5p2? 5p2 can have 5p2, two unpaired. What about 5p3? 5p3, there are three unpaired. Hunt's rule, you remember that? Then what about 5p4? 5p4, two unpaired. 1, 2, 3, 4, two unpaired. The 5p5, 5p5 again has one unpaired electron. One unpaired electron in 5p. 5p6, no unpaired electron because that's completely filled, all are paired. I hope you got it. Then they ask, they give the element with one unpaired 5p. Then it could be 5p1 or it can be 5p5. 5p1 or 5p5. But once I go to 5p1, it should be group 13 element. 5p1 group 13. You remember in periodic table, according to group wise, I gave general configuration. NS1 group 1, NS2 group 2. You remember? Group 13, what was it? NS2, NP1. So the NP1 configuration can be found group 13 element. Thereafter, 5p5 is found in group number 17. Group number 17, if you remember, general configuration I gave you, NS2, NP5. Periodic table group, according to group numbers, I gave you the common oxidation state, the electron configuration. To this one, then 13, P1, then 14, P2, 15, P3, 16, P4, 17, P5. Then I told you it can be 5P1 or it can be 5P5. Then it could be group 13 or group 17. But now the thing is this one. It's given like, the element with one unpaired 5p electron that forms a covalent compound with fluorine. Covalent compound with fluorine. There are group number 17. Actually, if we go to the possibilities, group 13, what are the elements here? If I write everything, you can't see that. Boron, aluminium, gallium, indium, like that. Right? Here, if I write fluorine, chlorine, bromine, iodine, astatine, like that. But, this is second period. Boron, fluorine, chlorine, third period. Bromine, fourth period. Iodine, fifth period. Then N equals 5. We talk about N equals 5. That means they ask these two, indium or iodine. N equals 5 means fifth period. Now I decide 5p1, 5p5 can be found group 13, 17. Then question is indium or iodine. It should form covalent bond with fluorine, this element. Then to make the covalent bond later in bonding, I will explain. Electronegativity difference between the two elements should be low. If it is 0, it's 100% covalent. 100% covalent. Right? But if it is very high, like 3 difference, electronegativity difference 3, like that, then there is ionic bond. High electronegativity difference, ionic. Then small value should be covalent. Then tell me, where do you find then large electronegativity difference between indium fluorine or fluorine iodine? These are metals, ne? Indium is a metal. metal and non-metal, non-metal and non-metal, metal, non-metal, non-metal, non-metal. Then if you consider covalent, the favorable one is non-metal, non-metal. Non-metal, non-metal, most probably you get covalent. Therefore, it should be iodine fluorine will make a covalent compound. Then they ask the element with one unpaired 5p electron that forms a covalent compound with fluorine. Then your answer should be iodine. That's the element. If you don't understand this, it's okay. Once I explain the ionic bond and compare ionic with covalent, I will explain how to predict whether it is ionic or how to predict whether it is covalent further. Right? B, the as yet undiscovered, the alkaline earth metal after radium. The alkaline earth metal after radium. Then just by referring the periodic table, you can find it. Alkaline earth metal after radium. What is right? The expected ground state electronic configuration. Beryllium, magnesium, calcium, strontium, radium. Radium is in 7th period. You remember then. Beryllium, magnesium, calcium, strontium, barium, radium. These are the alkaline earth metal, group 2. Group 2 general configuration, NS2. This is 2nd period, 3rd period, 4th period, 5th one, 6th one, and 7th one. Now they say the alkaline earth metal after radium means somewhere here. Let's say X or something. Then what about this one? Where do you find that element? That element is found in 8th period. It's not discovered yet. Right? Then if it is there, it should be definitely 8th period. 8th period means N equals 8. Then it should be 8s2. So the configuration should be 8s2. There's just the ground state electronic configuration for the following. The noble gas with electron, but the thing is this one, last one 8s2, then we have to complete the configuration up to 8s2. But in our syllabus, we don't have it. In our syllabus, we don't have it. At least you identify the last sub-energy level configuration, that's enough. Because to go to this one, we have to complete F orbit, F also. But fill in electron to F, we don't have it. No need to write complete configuration. At least you identify the last one, it's enough. C, the noble gas with electrons occupying 4d orbitals. Noble gases mean group 18. The configuration NS2 NP6. Helium I ignore. Helium is 1s2. Then I take helium, neon, argon, krypton, xenon, radon, and organosum. Sorry, what about this one? It's 5s. Sorry, this is second. 2s2, 2p6. This is 3s2, 3p6. This is 4s2, 4s2, 4p6. This is 5s2, 5p6. So like that. This is 6s2, 6p6. That's how we have the configuration. But they say the noble gas with electrons occupying 4d orbit. So once you come to 2p6, do you meet any d orbitals? No. Once you come to 3p6, do you meet any d orbitals? No. After 3p6, 4s1, 4s2, then only we come to d. Then once you come to 4p6, you meet d, of course. Here, before you come to 4p6, then 3d filled. Therefore, krypton is something which has electrons in 3d, but there's 4d. Then what is it? Xenon. In the case of xenon, before you come to 5p6, definitely you complete 5s2. After 5s2, 4d completed, then only you move forward. That means in xenon, 4d completed. There's the noble gas with electrons occupying 4d orbitals. Then, it should be xenon. I mean, you should write the configuration up to 5p6. The element is xenon, then write the configuration for 5p6. If B here, then I write C somewhere here. Then it's like 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6 after 4p6, 5s2 after 5s, it's 4d10. Thereafter 5p6. That's the configuration of Xenon. 5p6 after 5p, it's then 6x, 6s2. Thereafter we go to 4s. But here we don't have. Yeah, just write in configuration for xenon will be enough. The first row transition metal with the most unpaired electrons. First row transition metals with unpaired electrons. Transition metals means simply the exact definition for transition metal will be done in inorganic chemistry D block. So if you find the element and write the ground state configuration, you find at least one unpaired d electron, it's a transition. Or maybe in the element you don't find unpaired, then you go to the most stable oxidation state and write the configuration. You find the unpaired electron, unpaired d electron, one at least, then it's transition. You don't find unpaired in ground state atom. You don't find unpaired d electron in any of stable oxidation state. Then definitely it's non-transition. That's the definition. Simply, it's halfly filled d electron. This is applied for d block metals. First transition series mean, in the periodic table, it's about 3D transition. 3D series. If you carefully look at this is 18th D part. First transition metal series starting from scandium, 21 atomic number, then titanium, vanadium, chromium, manganese, iron, cobalt, copper, zinc. These are there's first row of transition. Yeah. But remember, zinc, according to that definition, it's not a transition. Zinc metal elemental form, you write the configuration, no half filled D, stable oxidation state +2. When you write the configuration for +2, no half filled D, therefore zinc can't be transition. Correct? Then it could be from scandium to copper, you have to check it. But they ask the first row transition metal with the most unpaired electrons. In scandium, when you write the configuration, maybe you remember it's 4s2 3d1. They ask unpaired electron. Then I told you in the class, completely filled, no unpaired. Then D1 means just one unpaired electron. D1, 1. Then this is 4s2 3d2. 3d2, how many? When you write it, 1, 2. Likewise, this is 3d3. There are 3 unpaired. What about chromium? It's 3d4, but will you get 3d4 final? No. I told you then 3d4 close to partial stabilization. Therefore, in the case of 4s2 3d4, this rearranged like 4s1 3d5. It takes one electron from 4s. I explained everything, energy variation and everything. First row transition metal with the most unpaired electron. 4s1 not completely filled. There is one unpaired electron. 3d5 not completely filled. Then 1, 2, 3, 4, 5. How many? 6 unpaired electrons available in the case of chromium. Here 2, here 1, here 6. Manganese 4s2 3d5. Now the 4s2 mean no unpaired electron. 3d5 mean just 5. This is 26 means 3d6. 3d6 means you complete 5 like this and then add 1 again here. How many? 4. This can have 3 because 3d7, 3. Then wait a minute, I missed one thing. Vanadium, chromium, manganese, nickel missing here. Nickel is there between copper and cobalt. 28. 28 mean 2. 28 mean 1, 2, D8. 1, 2, 3, 4, 5, 6, 7, 8 mean 2. Copper, there is 1. Zinc, we don't consider. They ask which element can have the highest, most unpaired electron? It should be chromium. But the question is this: write the expected ground state electron configuration. So you identify element like chromium. Then you write the ground state configuration. That's the answer. 1s2 2p6, 3s 3s2, 3p6. Thereafter 4s2 3d4. No, 4s1 3d5. Oh, you can write 3d5 here and 4s1 here. Doesn't matter. That's a configuration. Question number 18. That's the answer. Now we have come to the last question, 19th one, and test your confidence part. What is wrong with the following configurations for atoms in their ground state? What is the problem here? First one given 1s2, 2s2, 3s1 given. That's wrong. It doesn't obey Aufbau principle. According to Aufbau principle, it should be next available energy state. After 2s, what is it? It's 2p. Then we fill that electron to 2p, not 3s. Therefore, this is the correct configuration. In the case of B, what's the problem? You get neon. This is condensed electron configuration. 2s2, 2p3. So then, before 2s2, 2p3, we get the noble gas 1s2. Neon, it is 2s2, 2p6. Before 2p3, it can't be 2p6. Therefore, it's not the neon, the suitable noble gas. It should be helium, 1s2. Thereafter, you can write configuration 2s2, 2p3. So therefore, this is the correct configuration for this one. So in C, what's the problem? C, it's given neon. Again, condensed formula, 3s2, 3d5. 3s2, then 3d5. What is it? After 3s, then neon for 3s, okay, because neon up to 2p6. After that, 3s. After 3s, what's the next available energy state? 3p. Therefore, those 5 electrons should be added to 3p, not D. Therefore, this is wrong. This is correct. Got it? Then these 19 questions are given to develop your confidence in these sections. Atomic spectrum, quantum numbers, writing electron configuration, and yes, those are the things check. So if you to develop the confidence in these sections, these questions are given 19 questions. In the TUT, there are past paper questions. These questions not to develop the confidence. This is to test your confidence. Right? We will meet again under that section. Test your confidence part. You have given questions from 2008 to 2024. Okay. We will meet the next discussion part there.